people. Okay, so now I'm recording. So now anything that you type into the chat will be recorded. So if you want to put your name in now, I'll have a record that you're in attendance. I just see there's some back and forth going on the chat. Nobody has data. Zoom meeting. Oh, let me send ID is ID. Let me just send this 882.022.0889. Okay, so hopefully some more people will come in. Okay, welcome Alan, Armstrong, Ed, Joyce, Princeton, Richard, DC. It's good to see everybody here. Okay. Okay, maybe we'll wait 1 or 2 more minutes just for some people to enter the room because I just sent the address. Okay, well, and it's getting to be on the late side, so I think we should just start. People will come in as they come in. All right, so we're recording. So welcome everybody. Going to spend today. It's going to be kind of the last major day that we're talking about visual presentation of data, and soon we'll move on to other things. But for today, I want to finish the unit on histograms that we started last time. And I want to go in particular step by step in Microsoft Excel about how you make a histogram. So I'll have some instructions for that. And then I want to talk a little bit about cumulative relative frequencies and percentiles. Like we see percentile all the time. So we should have an actual formula that calculates percentile, and that tells us what it means. Okay, so that's the agenda for today. And then we'll have, I think, 2 or 3 more weeks of statistics where we'll talk about measures of central tendency and measures of dispersion and other things. So let me just mute everyone. Okay, so first, I just want to go over the homework exercises. And I think for this, it's going to be a little more convenient if I just kind of answer this just to make sure that we have enough time. So if you recall the homework exercise 1, we had a frequency distribution for commuting times to work in minutes from working adults in a county in California. And this is what we had, so 5,200 people commute 0 to 5 minutes to go to work, 18,200, 5 to up to 10 minutes, and so on. So the question is to add a column for relative frequency and then create a histogram for the data using relative frequency on the vertical axis. Okay, so with this histogram, I'm going to just draw it by hand. And then for the next one, we're going to use Microsoft Excel. So first, we need to have another column here for relative frequency. So let me add this here. And remember, we have the formula that relative frequency, this equals absolute frequency over total number of data points. Okay, so right, so the relative frequency is equal to the absolute frequency over the total number of data points. So based on this chart, how do we figure out the total number of data points? Because we're going to have to divide everything by that in order to figure out the absolute frequency. So I don't necessarily need an answer. I just want to know, what do we do with the numbers on this chart to figure out the total number of measurements that were taken, the total number of, in this case, it's the total number of people who were surveyed about their commute time. So what do we need to, how do we derive that from this chart over here? So 9. Okay, so I see the answer 9. So the 9, I assume you're referring to 9 rows in this chart, right? So those 9 rows represent the different frequency classes, right? Because there's lots of people who were surveyed and their commutes take lots of different amounts of time, we decided to group everything into classes. So we use 9 different classes, but that doesn't mean that 9 people were interviewed, right? Over here, we have 0 to under 5 minutes. So people who had less than a 5-minute commute to work, there's already 5,200 people who commuted less than 5 minutes to work. So what I'm really asking here is, what is the total number of people in this survey? So there's 9 classes, but what I want to do is the total number of data points. Total number of data points is a lot more than 9, right? So how do I figure out the total number of measurements here from this chart?
We need to add the entire total persons.
Exactly. So what am I adding up, Alan?
Yeah, so we need to add the 5,200, 18,200, and
good.
Add all the frequency, all the data available under the frequency. We need to add everything that will come out of the total.
Exactly, right? So the total number of measurements is the sum of everything in this frequency column, right? Because this is the frequency for each class. So to get the total number, we have to add up all of the frequencies, right? So let me just do that quickly. So 5,200 plus 18,200 plus 19,600 plus 15400 plus 13800 plus 5,700 plus 1020 plus 2,000 plus 2,000. Okay, so the total number, which I'll write down here, this total number is 90,300. Okay, so that's the total number over here. Okay, 90. I got it. Okay, so I got a different answer. Let me make sure that I did this correct. Oh no, you're right. You're right. 92.1. Yes, thank you. I forgot a 0 in one of my things. So yeah, so you were right, Princeton. It is 92,100 is the total number of data points. Okay, great. So for the relative frequency, we just have to take each of these numbers and divide it by 92,100, right? So we start with, 5,200 divided by 92,100, and maybe we'll round everything to 3 decimal places. So this over here, the relative frequency up here, this is 0.056, which I'll just write down here. What is that? That's 5,200 divided by 92,100. Okay, so I won't write this in every row, but we'll just figure the rest out. So we have 18,200 divided by 92,100. So this is going to be about 0.198, and then 19.6 divided by 921. So this is going to be 0.213, and then 154. This is going to be 0.167, 138. This is going to be 0.150, then 57. This is going to be 0.061. Here, the next one is 0.111, and then 2,000 for each of these. So this is going to be 0.021, and this, 0.022, and this is also going to be 0.022. Okay, so I just did those on a calculator. And so these are our relative frequencies, right? And what number should the relative frequencies all add up to? Like, without actually doing the addition, what number do the relative frequencies have to sum to? What has to be the sum? Any guesses? What do you think these, if I add up all of the numbers in this column, what do you think the sum should be?
So 0.1.
1. Yes, I see Lenovo. Yes. 1. Yes, that is correct, right? The answer is going to be 1. Can anybody explain? So, in fact, if you add these all up, you're going to get 1.002, but that's just because of rounding errors. If I used enough digits, it would add up to 1. So why do the relative frequencies have to all add up to 1? Can anybody give me an explanation?
Yeah.
Yep. Yeah, James?
Yeah.
Mm-hmm. Actually, no, never mind. No, these will add up to exactly 1. It's right. Can anybody give me an explanation for why the relative frequencies need to add up to 1? Well, let's think about it, right? What do we get this denominator from over here? This denominator, 92,100, is the sum of all of the frequencies. And so what is this number? This is 5,200 over 92,100. This is 18,200 over 92,100. This is 196,000. Sorry, this is 19,600 over 92,100, and so on. So when we add all of these numbers up, everyone has the frequency as the numerator and the total number of measurements, 92,100, as the denominator. So when you add them all up, they all have a common denominator. That's 92,100. And what are the numerators? It's all of the individual class measurements here. So when we add them all up in the numerator, it should be the same thing as the denominator, right? It should be the same thing as the denominator. So you add all of these up, and you're going to get 92,100 in the numerator, and the denominator is also 92,100. And so this is why it adds up to 1. And maybe more conceptually, the idea is each of these is giving the proportion of the total number of measurements. So this is saying that 0.056 of the people have a commute that's less than 5 minutes. Or in other words, 5.6% of the people have a commute less than 5 minutes. 19.8% have a commute between 5 and 10 minutes. 21.3% have a commute between 10 and 15 minutes. And so on, up to 2.2% having a commute between 40 and 45 minutes. So when you add up all those percentages, you've got to get 100%. That's going to be 1. Right. And so I see Princeton says it's 1 because all workers can either be later on time. Later on time doesn't really factor in here. No, this table doesn't tell us anything about whether people are late for work or whether they're on time for work. It just tells them how long it takes to get there, right? So we don't need to really talk about whether or not they're late. That's not relevant. What is relevant is that everything, all these percentages add up to the total number of people, which is 100%, which means as decimals, they're going to add up to 1. Okay. Is that clear? Any question on that? Okay. So let me just quickly draw a histogram here. It's not going to be the nicest histogram. I want to get through this one quickly so that we can draw so that we can do one for so we can do the next one, which will be on the computer. So let me just draw a quick kind of sloppy histogram. I'm going to write here, I'm going to say commute time. And then here I'm going to say relative frequency. Sorry, I don't have a lot of space on my sheet there, so I have to write relative frequency. So I'm going to put at my class divisions, I'm going to put little tick marks on the graph. So 5, 10, 15, 20, 25, 30, 35, 40, 45. Let's say, I think I don't need 50, right? Yeah, 45 is as high as it goes. So this is as far as I need to go. And now I'm going to have relative frequency. Well, it looks like my relative frequencies range from about 0.022 up to 0.213. So I want to pick a scale that's going to make these make sense in the graph. So maybe if the top of my graph should be maybe 0.25, and the bottom of the graph will be 0, and maybe I'll put a marking every 0.5, right? That's just a choice. You could mark it every 0.4 and have your graph go up to 0.24. There's lots of different choices you can make for the scale of your axis. But you just want to make sure that it goes high enough to contain the largest measurement, which in this case is 0.213. Okay, so I'm gonna do this. I'm gonna mark at 0.05, 0.10, 0.15, 0.20, and 0.25. And maybe let me just so it's not cluttered, let me just 0.25, let me just put relative frequency up here. Okay. So now I'm going to draw the bars. Well, for the range of 0 to 5, we have 0.56. So that bar is 0.056. So that bar is going to be a little bit higher than the 0.05 mark. Then we have 0.198 and then 0.213. So 0.198 is going to be up here, just a little bit below the 0.2. Then we have 0.213, so that's going to be a little bit above the 0.2. 0.167 is next. So that's going to be, maybe between here, 0.167 for 15 to 20. 20 to 25 is 0.150, so that'll be exactly right here at the 0.15 mark. 25 to 30 is 0.061, so that'll be a little bit above the 0.5 over here. 30 to 35 is 0.111, so 0.111, so that'll be roughly here. Again, this is all a little bit approximate and sloppy. We'll do a good one on a computer afterward. So 35 to 40 is 0.022, and then 40 to 45 is also 0.022. And if I want to, so this is 0 over here, let me just make this straighter. And if I want to, it can be nice to actually write the measurements in the graph. It can make it a little clearer. So I can write 0.056, 0.198, 0.213, 0.167, 0.150, 0.061, 0.111, 0.022, and 0.022. Right. Okay. So, all right. So this is my kind of not very pretty histogram, but we have low enough data that we can do it by hand. And if you want to make it look nicer, you can draw your lines straighter, or you can make things different colors or whatever. But this is the basic histogram. The idea is each bar corresponds to one of your classes, and the classes are evenly distributed from 0 up to 45, and we're using relative frequency as our y-axis here. Okay. All right, so any questions on this? I suppose I should say commute time. We should always give a unit when you make a histogram or a graph, so commute time should be minutes. All right. Okay, so let's go to the homework exercise 2, which will be a little bit more interesting because we're going to use we'll use Microsoft Excel to make the histogram. Okay, so let me just do this so it gets a little bigger. Okay. Okay, so the following data represents the total length of roads in miles in various subdivisions in the US. So we just have a bunch of numbers over here, and this data was used to help determine whether it would make more sense to build power lines above ground or underground. Okay, I think if there's more roads, it's easier to put them above ground. So it's a two-part. So first, we construct a stem and leaf plot for this data using the thousands digit as a stem. And then we'll construct a histogram for the data using these as our classes: 0 to less than 1,000, 1,000 to less than 2,000, 2,000 to less than 3,000, and so on. Okay, and we're going to construct that using Microsoft Excel. Now, after I wrote this problem, I realized there's a little issue using Excel for this, which is Excel doesn't like class numbers, doesn't like classes where you go up to a certain number, and you go up to less than a certain number. So Excel likes you to put in the maximum number in your class. So when we put in the maximum number in our class over here, instead of 1,000, we'll have to put in 999, and here we'll have to put in 1,999, and so on. Okay. So, but first, let's do the stem and leaf plot. This is easy enough to do by hand, right? So if we're using the thousands digit, we take, right, if we have stem, and then we have the leaves, right? Well, it's pretty easy to just look at the data and say, well, what do we have for the thousands digits? Well, we have some 3-digit entries, right? So there are going to be entries with a thousands digit of 0, and then we have 1, and we have 2, and we have 3, and it looks like we have at least one measurement with a 5. Oh, oopsie.
Hello.
Hello. Yeah.
Hello.
Sorry, question?
Yeah. Yeah, no,
Yes.
sir.
Yeah, roll, Prince? Yeah.
Yeah, for the stem and the leaf,
Yeah.
which one is actually first to be full? Is that a stem? Which one
The
is
stem is
actually
first.
to be full?
Yeah, well, usually you have to
Okay, then
decide
in finding the
where.
stem to be fresh.
Remember, you should think of it as not necessarily one is first and the other one is first, but you should think of it as you're going to make a split in your data at a consistent place value for all of them. So notice where I'm drawing these red lines. These red lines are always in front of the thousands place. So the red lines always, so in some sense, what they really have is the number of leaves, the number of digits in the leaf is the same for all of the red lines. So to put the red line in the thousands place, you always need a 3-digit leaf. Okay, because the line has to be the same place value for all of them.
Okay, so if for instance the place value is not seen, so definitely what would become the place value? Because where I'm seeing 510 is in 100 place and it's not in 1,000 place.
No, it is because it's in front of the thousands place here. You don't see it, but there's a 0 in the thousands place.
Stem for 510. Okay,
right.
So it becomes
right. So you see, for 510, I draw the line at the beginning of the number, whereas for these 4-digit numbers, I draw them after the first digit. Right. So the reason is, think of 510 as having a 0 before it. And so the line is always drawn between the thousandth place and the hundredth place.
Yeah,
okay, so place is going to be the stem, and everything else is going to be the leaf.
Okay, so just for simple understanding, every first digit in the list of the number, every first digit in the list of the number becomes a stem for that digit, right?
No, because 510, for instance, the first digit is a 5, but the 5 is not the stem, even though it's the first digit. This is why what you really have to do is you have to pick a number of digits to be the leaves. So when I say here, using the thousands digit as a stem, what that really means is you have to use the last 3 digits for the leaf. So if it's a 4-digit number, these last 3 digits are the leaf, and the 1 here is the stem. And if it's a 3-digit number, then it only has 3 digits. So all 3 of them are going to be the leaf. And then the stem, you have to just call it a 0. That's the only thing you can put there.
Okay. So
yes, you can't always use the first digit as the stem.
Okay, so definitely what you say is if for instance a set of data is given, let's say for instance in your 1,000 place and one is in 100 place, you just have to make it to be in your 1,000 place for everyone to be 1,000 place, so you can be able to find a stem. That way, just telling us, right?
Exactly. And the point is that you want to use it so that the stem is the first digit for most of your data. So in this data, most of the numbers are 4 digits. So it's a good idea to use the 3 digits as the leaf, and if there is a 4th digit, to use that as the stem. Right. So you want to pick it so that for most of the points in your data set, you're using 1 digit as the stem. But that doesn't mean that every point is going to have 1 digit as the stem. Right here, sometimes you have no stem at all. That's going to be a 0. Maybe we had another measurement that's 10,000. In that case, you'd have to use 2 digits as the stem. If it was 10,000, then the 10 would be the stem, and the last 3 would be the leaf in order to keep the place value. So it's always the same number of digits after the stem. The number of digits that make up the stem can vary depending on how big the numbers are.
Okay. Okay. Last question, sir. Before we
Yep.
go for, okay. Let's say, for instance, in a set of data that is given here, we have a number 4 to be among A. Let's say, for instance, we have 4 to be among A, and then in getting 4, just like a single number to be among A, what would become the stem onto A?
So if you had just a 4, like a single digit number.
Yeah.
So in that case, if it was a 4, the stem would just be 0 and the leaf would be 004.
Okay,
Just
thank you
put
so
in
much.
enough zeros to have that work. Yeah.
Thank you.
Okay, you're welcome. So let me just finish this plot. I'm sorry if this is going a little bit too below the screen. So we're going to use, just for an approximation for drawing this, we're going to use only one. We're only going to write down 1 digit for the leaf. So we're going to round to the hundreds place. So in this case with the 0, I need to see how many things are 3-digit numbers. So that's 360, 540. So I have meaning I'm going to use a 4 here because 360 rounds to 4. So I'm going to have a 4, 450 rounds to 500. So I'm going to have a 5. So a 4, a 5, 540 also rounds to 5, 510 also rounds to 5, 340 rounds to 3, and 240 rounds to 2. So I'm going to have a 4, a 5, a 5, a 5, a 3, and a 2. So maybe I'll put those in order. So that's going to be 2, 3, 4, 5, 5, 5. Those are my leaves there. I'm going to use only 1 digit. You could use more digits, but since the screen is not so big, I don't want to put in too many digits. So now for the ones, we've got 1280. That's going to round to 113 here. 1850 rounds to 19. So 13, 19. 1890 is another 19. 1250 is 13. 1240 is 12. 1000 is 10. So I think putting all that together, there's a 0, a 2. Let me this up. So it's a 0, a 2, a 3, a 3, and then a 0, a 2, a 3, a 3, and then a 9 and another 9. I think that's it. And then a 9 and a 9. Now we look for the 2000s. So what do we have there? We have 2250. That's 23. 2460 is 25. 2320 is 23. 2100 is 21. 2400 is 24. 2700 is 27. 2400 is another 24. And 2730 is another 27. So we've got a lot there. We've got a 1. And then I think we have 2, 3. It was a 3 and a 3. And then another, I want to make sure I'm not missing anything. Right. And then a 4 and a 4 for the 2 2400s, a 5 for the 2460. And then there was also a 7 and another 7. I think this is what we have for the 2s. Now we're going to go get less data. So for the stem 3, we're looking for things in the 3000s. This rounds to 34, 334, 32, 33, 34, and 32, and 31. So 3060 rounds to 31. So that's, you're going to have a 1, and then there is a 2 and a 2, and then I think there was 1, 3, 1, 3. And then I saw 3, 4 here, and 3, 4 here. So another 4 and another 4, and then a 9. And then 4, 4, 9. And then with starting with a 4, there's not much. I think the only data point is 4390 over here. So that should just be 4, 4. And then over here with the 5, the only data point I think is 5850. So that rounds to, oh no, there's 5320 and 5850. So this rounds to 5, 3, and this rounds to 5, 9. So we'll use that. So we got 3 and 9. Okay, so this is the stem and leaf plot for this data. And if you don't want to do it by hand, there are these websites from the notes last time that you can go to, and they'll make you the stem and leaf plot. But what I want to do instead, the stem and leaf plot you can do by hand. For histograms, it's really nice to be able to use a computer program. So last time I showed some websites you can go to for histograms. But if you have access to Microsoft Excel and you don't have access to the internet, then Excel will make a histogram for you. Okay, and it's pretty easy. I messed it up last time, but now I have the correct instructions. So before we do the histogram, any questions about the stem and leaf? So Princeton, I see not understanding how leaves have been connected.
Yes.
Is that okay?
Yes, sir.
Yeah, Prince?
No, sir. Yeah. Let's go to where you get a stem to be 4.
You mean this one over here, number 4?
And the leaves, like you're listening for the stem, where we get 4, 4, 3, 9, 0. But for 4, which is the stem, and then the leaves, you are listening, you only put 4 here. Why we don't, the other numbers are left here?
Right. So remember, so 4390 here is the only data point that starts with 4,000. So that's why we have the 4. And then the 390, if we're taking only the first digit, the 390 rounds to 400, right? Because it's a 3 and then there's a 9 after the 3, which makes it round up to the 4. So this is the nearest 100 to round this would be 4,400. So that's why we have a 4 in the stem and then we round to a 4 in the leaf.
Okay. So because it's to be run off, is why you just do that to become 4.
Exactly, right? So we have to round, with all of these, we have to round to the nearest 100 because I'm only writing 1 digit of each leaf here. So we've got to round to the nearest 100 so that we only use the first digit. And in order to do that, we have to round. So if we have after the 3, if we have 5, 6, 7, 8, or 9, we have to round it up. If we have 0, 1, 2, 3, or 4, we have to round it down. Is that okay?
Thank you. Yeah, it's honest too. Thank you so much.
Okay, you're welcome. Okay, great. Okay, so let's do this histogram on Excel. So let me show you how this works. So I've written a step-by-step thing that you can refer to later on if you're able to look at the notes. So we first put the data entries in one column. We put the maximum values for each frequency class in another column. And then we're going to click on data, data analysis, select histogram, and you'll be asked for a range of cells for the data and another range of cells for the bin. And you're going to input these using the format. You write down the top cell, and then you put a colon, and then you do the bottom cell. And then this will create a frequency table for the data. And if you want also to have a visual chart, to have a histogram, then we're going to check the box for chart output. Okay, so let me show you how we're going to do this. Okay, so I'm going to go to Microsoft Excel. Wait 1 second, I just need to see. I'm not using this. Okay. Okay, so let me go. So I've already put one thing here. Let me just delete the things that I have already. Okay, give me 1 second so I can show you my Excel. Okay, so let me mute everybody. Okay, so I'm going to share my screen with Excel. Okay, so can everybody see my Excel spreadsheet? Try to make it a little bigger.
Yes.
That's good? Okay. So so we don't have to waste the time, I already put all of the data into one column here on the spreadsheet. So this is just copying down the data that we have. So now for our bins, let's say I want to do, what I'm going to do is I'm going to put in the top measurement in each of my bins. So I think I'm going to shift it a little bit. So we're going to make the top measurement 1,000 in the first class, and then 2,000 in the next class, and then 3,000 in the next class, and so on. So we'll say 3,000, 4,000, 5,000, and then I'll say 6,000, because none of the measurements are bigger than 6,000, right? So I'm going to put this all in. Okay. So now what do? I click on data up here. And when I click on data, there's something all the way over here on the right that says data analysis. So I'm going to click on data analysis. Okay, click on data analysis. And so you see there's all of these tools for data analysis, and some of them make sense, and some of them maybe it's not clear what they mean, but histogram is one of the things on the menu. So I highlight, I can highlight whatever I want, but if I highlight histogram, then I click OK. And now, so it already has my input range. Don't worry about the dollar signs. You don't need them. So I can get rid of the dollar signs if I want to. You don't really need them. You can put them in if you want. Just to simplify it, I'm going to get rid of them. So what this shows is that my input range here is H1 to H30, right? My first data point here is in cell H1. Oh, what did I do? Sorry. So my first cell is H1, and then when I scroll down, the last cell over here is H30. Right? It's in the 30th row. And then my bin range, so Excel just calls bin, when we say frequency classes, Excel calls them bins. So my bin range is I1 to I6. This is telling me what all of the classes are. So the output range is just going to tell me where I want the chart to be printed. So let me print it in cell P1. So it'll be a little bit, maybe instead of P1, I'll print it in M1 so that it's close to my chart. I'll start printing it there. And now let me leave off cumulative percentage for now. Do I want chart output? And the answer is yes, I want chart output. Okay. I want to get a chart as well as a frequency table. So now I'm just going to click OK. And I'll drag this away and look what it has. So it has a frequency table. Now the bins are only, it doesn't say 0 to 1000. It just gives the maximum measurement in each bin. So this is maximum 1000, maximum 2000. This is 2001 to 3000, 3001 to 4000, 4001 to 5000, and 5001 to 6000. This is the frequency of each of them. And then it has another bin for more. Is there anything more than 6000? But in our case, there's nothing more than 6000. So it doesn't do anything more. So it gives me the frequency table, and then it also gives me a histogram for every bin, right? So it gives me a histogram for every bin. And if I click, I'm trying to remember, if I click on the histogram, I don't remember, if I click on chart design, it maybe gives me some options to make the bars look a little bit different. Give me a second. If I click on chart design, yeah. So if I click on chart design, I can click on various different choices, and all of the different choices just make the histogram look different. So sometimes they write the frequencies. You can write the frequencies on the bars. You can write the frequencies in the bars. You can write the frequencies, with a darker shade, or you can do it like this. So you have lots of different formats for your histogram. So you can play around with it and do whatever you want. There's even more formats over here. So you have a lot of choices. You can change the colors. I'm just clicking on all of these different formats that they have. But so you can take your favorite format, whatever you want. But the point is, it makes the frequency table for you and it makes the histogram for you. So I'm going to go back to a white background because I think it's a little bit easier to read. Okay, and actually I want to go back to the better axis scale. So it had a scale with 0s and 1s and 2s. Well, I don't remember. Okay, but this is fine. So the point is, this is how you make a histogram, and it's a number of steps, but I have the steps written out in the slides. So when I send the slides out, you'll be able to follow them if you have access to Excel. Okay. So any questions about this? And the important thing to make sure is that for each class, you enter the maximum number in the class as the bin. That's just how Excel does things. Not every program does things like this. Yes. For Excel, you have to put in the maximum number in order to get that. Okay. Okay, so let me stop my share here. Let me reshare my iPad. Got it. Content. Screen start. Okay. Okay. So great. Okay, so this is how we do histograms in Excel. So this is what I mentioned. We'll send this out if you want a reminder for how to do this. Okay, good. Okay, so I want to talk a little bit about cumulative relative frequency tables. Okay, and we'll do this again in Excel for our data. So suppose we have a relative frequency table for a set of numerical data, which is broken up into frequency classes, or, you know, as Excel calls them, bins. Oh, wait, sorry, what did I just do? Okay. So, so the cumulative relative, so we know what the relative frequency of a given class is, right? It's the number of measurements in that class divided by the total number of measurements. That's the cumulative relative, sorry, that's just the relative frequency. The cumulative relative frequency in a given class is the percentage or the proportion of the total data in that class, as well as in all lower classes. So if you want a formula, it's measurements in all classes below or equal to the given class divided by total number of measurements. Okay, so it's the measurements. So you look at the measurements in all classes below or equal to the given class, divided by the total number of measurements. Okay, as opposed to the standard relative frequency, which would just be the measurements in the given class divided by the total number of measurements. Okay, so cumulative relative frequency tables, you can make them by hand. You can also use them in Microsoft, make them in Microsoft Excel. And additionally, a line graph called a cumulative relative frequency plot can be added to the histogram to represent the cumulative frequencies. And what does this cumulative relative frequency plot have? It has a point for each class. So a point for each class corresponding to its cumulative relative frequency. And then these points are connected by lines. Okay. So let's look at an example which should make this all clearer. So let's say we're looking at this example from the homework. So so this is the same example. So this frequency table, I just copied it down. This is the frequency table from Excel. Okay, this is what Excel made. With Excel, it just called the bins 1,000, 2,000, 3,000, 4,000, 5,000, and then, you know, greater than 5,000, which was the same thing as the 6,000 bin. And here we're just writing it in a little bit more detail. Okay, so this is the road length, this was the frequency, and we can calculate the relative frequency over here. So in this case, this is the relative frequency. So the total measurements are equal to 7 plus 5 plus 8 plus 7 plus 1 plus 2. If you add this all up, you get 30. And so the relative frequencies are given by just dividing all of the absolute frequencies by 30, right? So this is equal to 7 divided by 30. This is 5 divided by 30. This is 8 divided by 30. This is 7 divided by 30. This is 1 divided by 30. And this is 2 divided by 30. Okay. Okay. All right. So let's add another column for cumulative relative frequency here. Okay, so I'm adding another column for cumulative relative frequency. And once you have the relative frequency, the cumulative relative frequency is easy to figure out because you just add up the relative frequencies for all of the classes up to your given class, right? So we start with, so for the lowest class, the relative frequency is the same thing as the cumulative relative frequency. So it's just going to be 0.233 here. For the next one, we have to add 0.233 to 0.167. So in this case, 0.233 plus 0.167, and that's going to be 0.400. And then after that, we keep going. So now we add 0.267. So this is going to be 0.400 plus 0.267. That's going to be 0.667. And then 0.667 plus 0.233. And that's going to be 0.900. Here we have 0.900 plus 0.033. That's going to be 0.933. And then lastly, 0.933 plus 0.067, and that's going to be 1. Okay, so at every stage, we have our cumulative relative frequency should go up, because for each class, the cumulative relative frequency includes all the lower classes. So every time you go up by one class, your frequency gets higher. And in the end, the cumulative relative frequency has to be 1 because it includes all of the classes, right? You're adding up all of the classes up to the end. And so remember what we said before, when you add up the relative frequencies in all of the classes together, you have to end up getting 1. Okay, so this is the cumulative relative frequency table. Okay. Questions on how to make the table? So at each row, you're just adding the new relative frequency to the previous cumulative relative frequency. Right here, we have 0.9 plus 0.33, the 0.033. The 0.9 comes from the previous cumulative relative frequency, and the 0.033 comes from the relative frequency in that row. Okay, so let me just show you how Excel can do this. Okay, so I'm gonna go back to Excel. Okay, so let's use the same data over here. I'm gonna delete this histogram. How do I delete it? Okay, good. So I'm gonna delete this histogram. So now I'm gonna do a new histogram, right? So I'm gonna do data analysis, histogram, okay. I have the same input range, H1 to H30, the same bin range, I1 to I6, same output range. I want to print it in M1. And now, what do? I just throw on, I just check the cumulative percentage box. That's the only thing that you have to change in order to make a cumulative frequency graph. Okay, so I check cumulative percentage, and I go, okay, that's fine. And now look what we have. So now it adds a cumulative column. It expresses it in terms of percentages. I expressed it in terms of a decimal, but it's easy to go between percentages and decimals. You just have to move the decimal point 2 spaces. So it has here 23.33%, 40%, 67%, 90, 93, and then 100%. And then what it does is it gives you the cumulative frequency plot. So what you see is it has the standard histogram over here. Let me try to make this a little bigger. Let me see if I can make this bigger just so it's easier to see. I want to make this bigger. Okay, let me just make the histogram bigger. Okay, so we have this bigger histogram. And so you have your standard histogram over here with all the classes, and then you have this cumulative orange line. And the scale for the orange line is on the right instead of on the left. So on the right, it has all of these percentages going up to 100%. And the cumulative percentage, remember, in the first class, it was 23%, and then 40%, and then 60, I think it was 67%, and then 90%, and then 93%, and then 100%. So that's telling you that if you're looking at jurisdictions up to 3,000 miles, those 3,000 miles contains, already like 67% of the jurisdictions. That's what this cumulative relative frequency plot tells you. It tells you overall what is the relative frequency of all of the classes up to and including the given class. Okay, so for Excel, it's very easy to make a cumulative relative frequency plot. You just have to check the extra box. When you do histogram, there's just an extra box to check for getting cumulative relative frequency, and you just have to check that box. Is that okay? Okay, that's okay. Let me close Excel. Let me get my iPad back on. Zoom. Okay. Okay. All right. Great. So good. Okay. So let's move on then, if there's no questions, for the last topic today, which is percentiles. Okay. So percentiles. So percentiles give a way to help understand a numerical data set. And they tend to work better with larger data sets. You know, so you can talk about like height and weight percentiles for children of a given age. Like this baby is in the 90th percentile for weight or the 80th percentile for height. And roughly what it means is that the nth percentile of the data set is the number below which n% of the data lie. So if you're at the 80th percentile, that means that 80% of the data are below that number. And it turns out that actually turning this into a precise definition, there's not only one way to do it, and different books give slightly different ways of doing this. And they're all pretty much close to each other, but there is not only one way to calculate percentiles, and different books and different computer programs use different ways to do it. So what is true is that all methods give approximately the same answer. The more data there is, the better the answers approximate each other. And so I'm going to give one method, which I think is the best, but might not be exactly the same
Dr.
that's used everywhere. Question, yeah, Ed?
Dr. Alton?
Yeah, Ed?
Yes, well, because what I've learned about percentile, I know percentile is used in determining the formation. Let's say maybe the performance of a person, in comparison.
Yeah.
Can I use percentile like that?
Yeah, as long as you have a full
set of tools.
Yeah, so if you want to do it like performance, academic performance, you mean?
Yes, yes.
Yeah, exactly. So if you have a list of grade point averages for a whole school, then you can talk about what is the 80th percentile grade point average, what's the 50th percentile grade point average, what's the 90th percentile. Yeah, so and it's really good to use percentiles for a small class. It's not as useful, but if you have a big class or a big school, then percentiles are a very reliable thing to use.
Okay, thank you.
You're welcome. I would say if you have only like 5 students, then percentile doesn't make much sense. Percentile is better if you have 50 students or 60 students. Okay, so let's do some actual formulas here. So the way that we're going to do the calculation is what's called the interpolation method. So the setup is, suppose we have a data set with n entries, and we want to calculate the pth percentile. So the first thing that we do is we arrange the data in ascending order from smallest to largest. Okay. Then we calculate what's called the rank of the pth percentile. So we do this with a given formula. So you take p divided by 100, that just turns it into a percent. Let's say we're trying to get like the 80th percentile. You take 80 divided by 100, that gives you 0.8, and you multiply it by n plus 1, where n is the number of entries. So this is the formula we use for that. And so now what do we say? Well, if this rank happens to be an integer, then the pth percentile is simply the rth data entry. So if we had like, 49 data points and we were looking for the 80th percentile, then we would take 80 divided by 100 is 0.8. we would multiply it by 49 plus 1, which is 50. 0.8 times 50 is equal to 40. So R would be 40. And in that case, if it's an integer, we would just list all of the data, and we would take the 40th entry in the list. Okay, that's how we do it. Now, if R is not an integer, then it gets a little bit more complicated. And this is where there's different methods that do different things. So if R is not an integer, then you have to look at both the rth. So I guess what I should really say is what we're really doing is taking the floor function. We have to look at both the rth and the R plus first data entries. So if R, for example, if R equals like 3.75, look at both the third and the fourth data entries. Okay. And so then we let F be the fractional part of R. So that means if R is 3.75, then the fractional part in this case would be, F equals 0.75. It's just the part after the decimal point. Okay. So if we have this, yes, by the way, Koi, yes, I will certainly send the PDF afterward to everybody. And in this case, the pth percentile, I guess I should say here, the pth percentile is given by the following formula. You take X, which is the third data entry, and then you add the fractional part times the difference between Y and X. This is what's called interpolation. Okay, and this is why this is what's called interpolation. This is why the method is called the interpolation method. Okay, so that's a lot to do. So let's do it step by step, so we can figure out, so we can get a little practice. Okay, so let's do an example. We'll go for everything. So let's consider a class whose scores on a quiz are given by the following frequency table. So this is a quiz out of 10 points. So 2 students scored a 4. 4 students scored a 5. 3 students scored a 6. 3 students scored a 7. 2 students scored an 8. 3 students scored a 9. And 3 students scored a 10. And the goal and the question is to calculate both the 30th and the 50th percentile of this data. So on this page, we'll do the 30th, and then on the next page, we'll do the 50th. Okay? Okay, so 30th percentile. Well, first we need to calculate n. So remember, so n is the total number of data points. And so what is that in this case? How many total data points are there in this data set? It's a question of how you can read frequency tables.
1, 2, 3, 4, 5, 6, 7.
There are not 7 data points. There are 7 categories, seven numerical data results, but that's not the number of data points, right? Each student is a data point. 20,
Okay,
exactly,
then,
right?
20.
Yeah, 20, because you have to add everything in the frequency column.
Hey,
Right?
20.
Exactly, thanks, Ed. 20, Ed, that's correct. Yeah, so, right, so there's 20 because you have to add up all the frequencies, because each frequency represents that number of students, right? So you have to add them all up to get the number of data points. So in this case, this is 2 plus 4 plus 3 plus 3 plus 2 plus 3 plus 3. That's equal to 20. Okay, so now we have to calculate R. If you recall this formula, so R is the rank of the pth percentile. We take P over 100 times n plus 1. So in this case, R is going to be 30 divided by 100 times 20 plus 1. So that's 3/10 times 21, which is equal to 63 divided by 10, which is equal to 6.3. Okay, so that's our rank here, is 6.3. Now, what do I do with the data? Here we have small enough data that I can just write them all out in ascending order, right? So I can just write out 4, 4, because we have 2 4s, 5, 5, 5, 5, 6, 6, 6, 3 sixes, 7, 7, 7, 3 sevens, 8, 8, 9, 9, 9, 10, 10, 10. Right, so that's my data here. So what do we do with 6.3? We have to look at both the 6th and the 7th data entry. So 1, 2, 3, 4, 5, 6. Okay, so that's the 6th data entry is a 5, and the 7th data entry is a 6. Right, so if we look at the notation I used over here, we called that X and Y. So what we would take here is we would have X equals 5 and Y equals 6. This is going to be 6th entry, and this here is going to be the 7th entry. Okay. And then lastly, we have to use the interpolation formula. So it's really kind of like 4 steps, right? We have to calculate N, calculate R, write out the data, and then do the interpolation formula. The interpolation formula says the 30th percentile is going to be X plus F times Y minus X, where F is the fractional part, right, of R. So in this case, we have, X plus F times Y minus X, which is going to be 5 plus, well, what's the fractional part of R over here? The fractional part is 0.3, whatever goes after, exactly. Yes, thank you, Gabriel, right? It's whatever goes after the decimal point. So 5 plus 0.3 times 6 minus 5. And that's just 0.3 times 1, so this turns out to be 5.3. Okay, so the 30th percentile, this is the 30th percentile. Okay. So the 30th percentile of this data is 5.3 using the interpolation method. There are other methods which say you just round R to the nearest integer and use that. So in that case, you would just round 6.3 to 6 and say the 30th percentile is 5. That has the advantage of always giving you an element of your data set. But I think the interpolation formula tends to give a better picture of your data. So I like the interpolation method, which would say the 30th percentile would be 5.3. Okay, if you're listing. And this is how Excel does it if you use it to calculate percentiles. Okay, so the process, it's multi-step. So you have to do quite a few things. But this is for 30th percentile. We'll do 50th percentile also. But before that, any questions on this calculation?
Yes, I have a question.
Mm-hmm. Yeah, Ed?
So why if I had like 10 students in the class and everybody's got individual grades?
Right. That's fine.
Yes. So then how will I calculate percentile?
You can just do it the same way. So if you have 10 students, all that is would just be a frequency table where every frequency is a 1, right? Because you're having only one student with each grade. And so then you just do the same thing. You'd write down all the data, but you'd only include each grade once because each of the students do their own individual grades. And then you just use exactly the same method. You'd have N would be the total number of students. You'd calculate R the same way. You'd write down your data, and then you use exactly the same formula.
Okay, thank you.
Okay, so we can do an example of that. Actually, I'm trying to remember on the homework. Yeah, so on the homework, there will be, what did I want to, no. Okay, no, we'll do an example of that next time. Okay, we'll do an example where everything is individual. Okay. So let's just, for one more practice, let's just do the 50th percentile also, right? So the same thing. So yes, Princeton, 0.3 is the constant for F. Remember, F stands for fraction. It's the fractional part. And so you're taking only what's after the decimal point. So it's just the 0.3. Okay, so let's do the same data set, but let's do the 50th percentile. So 50th percentile. So 50th percentile. Okay, so we still have N equals 20 because it's the same data. So for R, we use the same formula as we had over here, but instead of 30 over 100, we use 50 over 100, right? Because we use the percentile up here. This is P. So R is equal to 50 over 100 times 20 plus 1. Well, 50 over 100 is just 1/2, so that's just 1/2 times 21, which is 21 over 2, which is 10.5. Okay. Okay, great. So the rank is, so 21 over 2, it's at 10.5 for the 50th percentile, right? So now we have the data. Maybe I'll just write it out again. So data is 4, 4, 5, 5, 5, 5, 6, 6, 6, 7, 7, 7. What was it? 8, 8, 9, 9, 9, 10, 10, 10. 8, 8, 9, 9, 9, 10, 10, 10. So since it's 10.5, we have to look at the 10th and the 11th data entries. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10th data entry is the 7, and the 11th data entry is also a 7. So in this case, we have x equals 7 and y equals 7. So when the entries are the same, the percentile is just going to be 7, right? The 50th percentile is just going to be the same 7. And the way and the way we can, but even with the interpolation formula, it'll still work. So if I do the interpolation formula, what do we have? We have that the 50th percentile equals, well, we start with x, so 7, and then plus the fractional part, that's 0.5. 7 plus 0.5 times, and now we have y minus x, but y is 7 and x is 7. So it's just 7 minus 7, which is just 0, right? This is just equal to 0. So in the end, we just have 7, okay, which is going to be the 50th percentile. Okay, so in fact, when x and y match, when your rank falls in between two data entries that are the same, then the percentile is always just going to be that number, whatever it is, okay? And 50th percentile has another name that we'll talk about next time. 50th percentile is also called the median. And this is, in fact, exactly how you calculate the median. When you're looking for the median of a data set with an odd number with an even number of data entries, you take the two middle entries and you take their average. That's, in fact, exactly what this interpolation formula does. So we'll see next time that this is equivalent to calculating the median when you do this method for the 50th percentile. It's the same thing as calculating the median. Okay, any questions?
Yes.
Yeah.
Yes, yeah.
James?
Yes.
Yeah. Question? Yeah, Prince?
Yeah, the data, small issue with the data collected here. Yeah, why you just to start with 4 and then even the 5 appearing 4 times, what if 4 appearing only 2 times? So what is happening?
Oh, that's just, this is how the data was given to you. We're saying, let's say you had a class that got quiz scores and 2 people got a 4 and 4 people got a 5, 3 people got a 6 and so on. So it's given to you from this frequency table. It's telling you how many 4s, how many 5s, and how many 6s and so on. I mean, I just made the data up. There's no, there's no, but you could do this with whatever your data is from whatever class you teach. Yeah. Yeah, Alan?
Yes.
Yeah.
Okay, so definitely the percentile here, it means 100, right? Which is derived from percentage or percent.
Yeah, it's a percentile. It's not the same as a percentage, but that's why we call it the 30th percentile instead of the 0.3 percentile, right? Because calling it the 30th is using a percentage, right? It's basically the score where 30% of the scores are lower. That's why we call it percentile, because 30% of the scores are going to be lower.
Yeah,
And if you really have lots of data, like you have thousands of data points, then this really becomes exactly accurate, and the interpolation will never really matter that much. The interpolation is important when you only have 20 data points, when you don't have a very large data set.
Yeah,
Okay, thank you.
Yeah, you're welcome. Prince, did you have another question?
I
Yes.
also have a
Oh, sorry,
question.
James.
Yeah, I really want to know how we call the rank.
The rank is
rank.
with this formula here. So it's the percentile divided by 100 times n plus 1, where n is the total number of data entries. So this is the formula for the rank.
Oh, okay.
Okay.
All right.
All right,
Thank you.
You're welcome. Other questions?
Yes, I have a question.
Yes, Alan.
I think you in the first example we saw that our data lies between a 6 and a 6.
No, I
then
think the first example, it should be between a 5 and a 6, because it's the 6th entry and the 7th entry. So the 6th entry is 5 and the 7th entry is 6.
Oh, all right. Okay. All right.
Yeah. Okay, no problem. Other questions? Okay, so we're just about out of time, but let me just say something very quickly. So percentiles are related to cumulative relative frequency. So in particular, if the cumulative relative frequency of a class is p, then if let's say the cumulative relative frequency is like 0.4, then the 100th percentile, so if it's 0.4, you'd look at the 40th percentile, that's just converting to percents, of the data should be roughly the maximum in that class. So maybe we don't have time to do this right now. But with the second example from the homework, so the idea is, let's look at cumulative relative frequency 0.4. So if we go back to this example, over here, we had for the second class, the cumulative relative frequency is 0.4. Okay? So the point is, we expect the 40th percentile to be about 2,000. And we expect the 66.7th percentile or the 67th percentile to be about 3,000. And we expect the 90th percentile to be about 4,000. Okay, so I think we don't have time now to actually do the calculations. Maybe I'll save them for next time. But over here, without doing any calculation, we expect the 40th percentile to be about 2,000. Okay, so we'll do the calculation next time, just because we're out of time. So we'll do the calculation. Next time. But we'll see. And the idea is, what's a percentile? A percentile means 40% of the scores or of the data are below that number. So when you have a cumulative relative frequency table, if the cumulative relative frequency is 0.4 for the second class, that means about 40% of the scores or of the data are in these first two classes. So the number that separates the 40% from everything else should be basically near the top of this class. The top of this class is going to be when you have 40% of the scores below. So we'll see, we'll calculate it for this data that the 40th percentile is not exactly 2,000, but it's going to be pretty close to 2,000. So we generally expect that to work. Okay, good. So we'll do the calculation next time. So there are a couple of homework exercises. So using the frequency table from this slide number 9, the quiz scores, right? So this is just this frequency table over here, which I'll send. So I want you to just do a few more things from that. So first, add a column to the frequency table for the relative frequency and the cumulative relative frequency. Construct a histogram for the data, as well as a cumulative relative frequency plot. This is maybe if you have Excel, this is easier, but you can do the histogram by hand. And then calculate the 60th and the 70th percentiles for the data. Okay, so all of them for the same data set that we had before. Okay, so next time, I'll send this out later today. So next time we'll do this example where we calculate the percentile, which we expect to be about 2000. And then next time we'll discuss measures of central tendency. And another thing, this is not on the syllabus, so I wanted to mention that class will again be 1 hour early next week. Okay, because I have to be somewhere at 1 o'clock Eastern time. So class will again be at 3:30 next week instead of at 4:30. Okay. All right. So thank you all for your attention. And I will stop the recording now.